Okay. All right. So, hello everyone. Thank you so much for being here to attend my research talk today. And yeah, today we are going to look at how we can leverage reinforcement learning in the context of design. And the operative word here in my title also is design. And in the context of, in the optimization sense, what do you guys think design means? That if you want to solve an optimization problem to design something, what does that mean?
Getting the architecture correct.
But in the how do you formulate that as an optimization problem?
Design what you want to optimize itself, like what function and all that.
Okay, I was thinking a little bit more differently. Yeah, so design in this in the context of my research here, the design actually means to set I mean, it has two different meanings. Okay, the first one is you have some sort of design variables, and in the space of those design variables, you want to have certain configuration that you want to find, right? Or it's a more direct kind of a search problem itself, where you have this large space of various subgraphs within a graph or something like that, where you want to perform a search and you want to find the desired subgraph in this space or the desired configuration in the space of the design variables, right? So in terms of architecture, you would formulate it as an optimization problem, for example, like the number of layers that you have in your neural network, right? Or something like the number of neurons in each layer, right? So those are your design variables, and the right or the desired configuration would be probably something that performs the best, right?
Yeah.
And you choose among the various different possibilities, you just choose one of them, and that's the desired one that you wanted to design, right? So whenever you're doing yeah, so in my research context, this design problem is actually disguised as it's a search problem disguised as a design problem, right? And whenever you have this notion of search, then well, one of the questions that comes up is how big is this search, right? And so there's this number 10 to the power 80, and this is the total number of atoms in the observable universe, right? And do you guys know about this AlphaGo algorithm? Have you guys heard of it?
Yeah.
And so in that AlphaGo algorithm, when they were playing the game of Go against a human world champion, the number of possible combinations that they had was 10 to the power 170, right? And that's actually the size here is not up to scale. 10 to the power 170 is actually much, much bigger than 10 to the power 80, right? And in the specific one instance of the search problem that I am solving, the number of combinations that can occur is actually 10 powers 116, right? So that's how big of a search problem that it is. And if I were to just evaluate each possible combinations, the universe would cease to exist before I could finish those combinations, right? So we want there to be some intelligent strategy to be used to narrow that search space and then get to our desired configuration or a subgraph, right? Yeah, so why does such a large search space occur in the first place? So there's this phenomenon called combinatorial explosion. Have you guys heard of this before? Right, so basically it means that because the search space grows exponentially with respect to the uh, number of things that you have in your configuration, actually the problem grows to really large values, right? For example, in uh, in the case of alpha transit, where we are given a city graph, and then our goal is to design a transit route, for example, a bus route, by extending one node at a time. Based on how many nodes you are looking at, the number of combinations actually increases massively, right? So in this network, first assume that the degree of each node is 3, and at level 0, the possible number of combinations that you can have is just 1, right? If you want to extend that to level 1, you have 3 combinations. If you want to extend that to level 2, you have 9. At level 3, you have 27 different combinations. And if we were to plot this, it would quickly get to some astronomical numbers just by expanding to up to 8 levels, right? And if yeah, in my case, actually, in my research, what I do is actually I designed 3 separate routes in one problem, and in the larger problem, I designed 16 routes, and each route is like the length 14. And when you do a really complex calculation of how many possible combinations that can give, the number I got to was 10 to the power 160. Okay, so the research objective here is to solve this search problem using two different approaches: end-to-end reinforcement learning and heuristic search algorithm called Monte Carlo tree search. Do you guys have you guys heard of this before? Where did you hear about it? Yeah, so actually, I also mentioned this earlier in my upper confidence bound, like exploration strategies lecture, right? And this is the algorithm that they use to play the game of Go in AlphaGo and yeah, win against the world champion, right? And the other thing is I want to evaluate those designs that I obtain from these algorithms against various different baselines, such as the real world human designed network and some other heuristics, and do some qualitative and quantitative analysis of those designs. And I've actually, in terms of my research progress, I've completed that part. And currently I am implementing this part. And so the rest of the lecture, I wanted to take the opportunity to actually do a deep dive into this algorithm and how it works, right? So that you guys, if you were to encounter such a search problem, later in your career or something, then you can probably refer to what you learned today. And so moving forward, I mean, I'm not going to talk as much about my research, but rather talk about this problem and this algorithm itself. Okay. So first, we are going to be taking a look at the basic version, the vanilla version of this algorithm. And let's actually start with the name itself. So fun fact, Monte Carlo is actually a name of a casino, and literally it means Mount Charles in Italian. It's a casino that's located in this country called Monaco. And the story is that the guy who came up with this algorithm had an uncle who was addicted to gambling or something, and then so he decided to name the algorithm after the gambler's favorite casino. And essentially, the idea is that we want to make decisions under uncertainty, right? And then in order to estimate that uncertainty, we do random sampling. That's the very high level idea of this algorithm, right? And for example, in one of my earlier projects, I had used this Monte Carlo method. I had used Monte Carlo sampling to estimate the entropy of a Gaussian mixture model. So if you guys remember from the same exploration strategies lecture, that if you had to estimate the entropy of a distribution, what you would do is you would take the product of probability and the log probability, and then you would sum over all the possible discrete distribution items, right? And in a discrete distribution, you would do a sum, but in a continuous distribution like this, you'd actually do an integration, right? But the problem here is that the way these Gaussian distributions mix with each other and reinforce each other in some places, and probably even cancel each other in some other places, it actually forms a really complex kind of a fabric that's laid on top of these Gaussian distributions, right? And there's actually, I forgot the specific problem, but there's actually some problem that how these exponentials and logarithms interact with each other. It creates some problem for integration. So one way to estimate the entropy of this is to do Monte Carlo sampling, where yeah, I basically draw random samples from this distribution, and then the more samples that I draw, the more accurate my entropy estimation gets, right? And yeah. And then the number of samples that are drawn from, like, this is basically a two-dimensional Gaussian mixture model where one x dimension is position, y dimension is width, and the height of this distribution is the probability with which a sample is drawn from this distribution, right? And you can see that uh, around the peaks, there's more number of samples being drawn, and that's likely what you would expect as well, right? Yeah, so if I were to increase the number of samples I drew from that, my estimate would get better and better. Okay, so the other part of this algorithm's name, there's tree search, the second half of this name, right? And uh, usually this algorithm works by representing things in a graph, and a tree is a special type of graph. And then when we're performing this search, we have to traverse this tree in some specific order to find the best or the optimal outcome. And that's why the name has tree search. So Monte Carlo tree search as a whole, basically it's a way to make good decisions when there are huge number of possibilities, right? And it's a heuristic search algorithm. The heuristic itself is random sampling is the heuristic, right? And it doesn't guarantee that you'll get a good solution, but you'll get a, probably a very good solution while using far less computation than using exact methods or evaluating every possible, every possible combination till the end of the universe, right? And the action selection mechanism that this algorithm uses is upper confidence bound one. And it's the same thing that we discussed in our exploration strategies lecture. So let's look at an example. Let's say you have this graph, and this graph is a universal representation. It could be anything like you're playing a game or something where you start your game of chess at the empty board, and then you have, for now, assume that you only have two moves that you can make, but in reality, there could be multiple different moves, right? And then every move leads to an extension of that move to other possibilities as well. Or in the case of transit route network design, you start your design at some transit center, like a bus center or something, and then you expand to various different landmarks in the city, and then it gives you more possibilities to expand and things like that. So at every node, you maintain a certain statistic. For example, in this case, the number of times you visited that node and the cumulative reward that you got through that node, right? For example, in this case, 16 times the root node was visited, and then you got, like, if it's a game of chess where it's a win-loss 0-1 reward, 7 of those times the game was actually won, right? That's what these values mean. And yeah, let's look at how we got to that, how we start from the root and then traverse to the leaf or the boundary of the unvisited nodes in that graph. So we have this root, and there are two possibilities. We use the formula from the exploration strategies lecture, the upper confidence bound formula, where the first part here is controlling how much it's kind of, you can understand intuitively this as exploitation, because it's the ratio. If we were to just look at the first part of the algorithm to decide which of these children to pick, then it would look at how many of those games that were played in total were won by the children, and that would be your pick, right? In this case, you'd pick B, right? Because that's 0.5% of the time the games were won, and A is smaller than 0.5. But there's this other term that controls the exploration, where you look at how many times each child was visited versus how many times the parent was visited, and that's actually in the logarithm. And one naturally very good thing about this action selection mechanism is that as the number of visits, as the number of total times you play the game increases, this second term actually gradually decays itself naturally, right? Without you having to employ a separate kind of annealing algorithm for this C parameter. Yeah, so exploration and exploitation, you can kind of understand it in those terms. And if we were to evaluate, we'd get B in this case, because it evaluates to a higher value of upper confidence bound, meaning that B has a higher potential to get the final outcome to be higher compared to A. So you go to B, and then you repeat the same process again. And now it turns out E is a better choice. So following this, you have to first go to the boundary of the visited nodes, right? And then now comes the second part of the algorithm, where you expand these nodes, right? And in this case, since the children of this E has not been visited yet, the upper confidence bound actually evaluates to infinity. They could be infinitely put in, like they could get infinitely higher reward. So what do you do then? Yeah, right. So the main heuristic behind this algorithm was to do random things, right? And the heuristic is to just pick one randomly. And yeah, so you extend this process till you hit some kind of a terminal node, right, where you would basically end the game. And then you either win or lose that game. And also, we don't store beyond the single node extension. Sorry, you don't store all the other random moves you make till you get to the terminal node. And you simulate in terms of transit network design. I'd have to take this design, take it somewhere to a traffic simulator, and then simulate and get some kind of a reward, right? But in if you're playing a game, then you wouldn't need this extra simulation step. As soon as you hit the terminal node, you'd either lose that game or you win that game, and then you get the reward, right? And then you back propagate that reward. And in this case, although the standard terminology used is back propagate, it's actually not the standard neural network terminology of back propagate where you update the weights. You're just updating the statistics of those visited. The node that led up to this, boundary node, all the parent nodes that led up to this boundary node, the statistics of those are updated, and you repeat the same process over and over again. Yeah, I know it's probably a lot. Any questions so far? Uh, yeah, also, to be honest, this was my first pass through this algorithm. So probably I'm not able to give as much intuition about why things are done. And I'm just here to tell you what things are done. And yeah, that's how I plan this. Okay, so basically we went through four different processes, right? We first looked at the selection mechanism where you use that upper confidence bound formula, and then you expand that by adding a new child node. If you're at the boundary, you pick randomly, and then potentially you'd have to simulate to obtain the reward, and then you update the statistics, right? So we repeat this process until some kind of a criteria is met. I mean, it could be like run the iteration for 800 times, or like run for these many hours or something like that. And then after you complete these iterations, you'd obtain a policy by looking at the visit counts. Looking at, so in this case, what would the policy be? What would the final policy, obtained policy be?
So whatever's been visited the most.
Yeah, so it would be go start at the root, go to A, and then go to D, right? That's the final policy obtained. If you were to just do that, obtain a policy based on these statistics, but you would ideally simulate it many, many times, something like 1,000 or 800. I mean, in the case of my sampling earlier, I had 400 different random samples drawn, right? So that is the algorithm. And now we actually come to, that's not even the hard part of the algorithm. That was the vanilla version of the algorithm, right? Now we'll look at how uh, Google, how DeepMind used that algorithm in their AlphaZero setup, right? Actually, there was this interesting documentary out last week. Did you guys watch? And if you watched a documentary called The Thinking Machine?
Yeah.
And the documentary focuses on the work of Demis Hassabis, right? And the first time, this the big moment in AI that Demis Hassabis created was this algorithm, actually, right? AlphaZero, where they made headlines all over the world, where a guy named Lee Sedol played against this AlphaZero algorithm.
Wasn't it AlphaGo?
Yeah, actually, it was a previous version of the algorithm, and then they actually, it's so confusing. If you look at this paper, they have four versions of this paper, I believe. The first one uses some human data, and then the later one reduces the human data, and then there's this AlphaZero, which actually uses no human data. And then actually, in terms of the state of the art, compared to the AlphaGo and others, AlphaZero is the state of the art. And the contributing factor for that is a mechanism known as self-play. And we'll take a look at self-play as well later. So yeah, so this actually is a very big moment in the entirety of the AI itself.
So the MCTS algorithm that we are now going to discuss is based on the AlphaZero, not the AlphaGo paper then?
Yeah, this is AlphaZero implementation. Yeah. So yeah, so the main difference is that if you notice in our previous version, vanilla version of the algorithm, there were no neural networks, right? We were just looking at some counts, and by looking at those counts, you call something a policy, and then you just use that to decide what to do. But there was no actual policy there. It was just a bunch of counts, right? And in this case, though, they actually do make use of a neural network which has two separate heads and a common body. And one head is called a predictor neural network, and the other is a value or a critic neural network. And the action selection mechanism in the previous one, we used to call it upper confidence bound, but here we call it predictor of upper confidence trees. And it's just because in that calculation formula, the output of this actor or the predictor is involved. And confidence trees because we're traversing the trees here, right? Okay, so let's look at the same graph again. And now the action selection starting from the root, the formula changes a little bit. This constant C is the same as previous one. It just has some extra words to represent it. But the interesting part is that it has now two major changes, which one of them is this probability, which is known as prior. And this prior, actually it's called prior because before we even make the selection, the value network has some preconceived notion of what the probability, how the probabilities should be distributed among those actions, right? That's why it's called prior. And then there's this 1 plus term in this denominator here, and that we'll see that actually prevents our division by zero error, and it actually prevents these PUCT values from becoming infinite like earlier. And that actually leads to an interesting case where the policy network will actually guide learning, and we won't have to do this random sampling. We will take a look at an example later.
Wouldn't the first part still evaluate to infinity? The first two?
Actually, it would, I think, yeah. Huh. Yeah, actually, it would. Did I miss that? Let's see what I do in the calculation later. Okay. Yeah, it would. Yeah, it would, but I seem to have ignored that. But I think they do ignore that. Ignore the first part. If it's an unvisited node, actually, I think the way it's implemented, I'll have to go back and look at the algorithm again. But I think if it's an unvisited node where the child's uh, visit count is 0, they actually ignore this part. Okay, so this probability actually comes from a neural network, right? There's a neural network which takes in the input state and then has two heads. One of them is outputting the probabilities for the two possible actions, right? Now, if we were to move forward with this algorithm, the action selection would be something like this. Here, one interesting thing is, although B had a lower prior probability, it ended up being chosen, right? And that could happen because of the other factors. And we repeat this process with the same, again, these probabilities here are actually obtained from the neural network. And when you get to the edge of the visited node boundary, you end up with two different branches again. In this case, we actually, oh, that's right. This would actually evaluate to something undefined, right? It's actually not infinity, it's undefined. And the 1 plus prevents this 0, this denominator term to become not infinite. And we end up with these two values, which are actually purely guided by what the neural network thinks is the better choice between these two, right? And in our previous vanilla version, we would actually extend this term all the way to the terminal node, and then we would simulate it and then get a reward, right? But in the AlphaZero version, we take the current state and then we input it to the neural network again, this time the critic part of it, and then we get the value. And we use this value again to back propagate the statistics that we have collected, starting from the root to the edge of the visited nodes. Yeah. Yeah, so that was just the action selection mechanism. But but how are these value and policy networks even trained? We didn't even discuss that, right? So we'd have to look at, we were looking at the innermost core part of the algorithm. We'd have to zoom out a little bit and look at how the rest of the things are set up in order to be able to do that. And we'll do that now. So let's say you ran the same graph, you ran the same simulation for 800 iterations. And then your latest statistics are something like this, right? Now, the second part of the algorithm is to obtain the policy, right? We'll look at how to obtain a policy. And basically, what is a policy? A policy is the distribution across the actions that you have given this state, right? And yeah, we use those statistics in this case. If you were to calculate the visit count, you'll actually obtain like action A has a probability 65%, action B has 35%. After you obtain this distribution, you'd sample and then you choose one of the actions. And interestingly enough, all this is done just for you to transition from the root to the first node. You then store the state, the policy, and a placeholder for the value that you'll replace later, and you discard everything else. You discard the entire tree, and then you transition to that node that you thought was the best one to go from the root to the first child, and then you run 800 simulations again, and you obtain another policy. In this case, you'd sample the policy to obtain something like the D is the next extension, and you'd again store that transition with a placeholder, and you'd repeat this process until you terminate. Then you take this, what the policy thinks is an optimal path to traverse, you'd simulate and get a reward. You'd replace all those placeholders with this reward value. And once you have your memory buffer, full of a bunch of transitions, you can use those transitions to calculate the policy loss, which is basically a cross entropy loss, a negative log likelihood. And so in essence, what's happening here is that you use Monte Carlo tree search to gather some data. And then what's happening here is that you make that policy mimic whatever Monte Carlo tree search had done, right? So now, without having to do all these simulations, the policy actually learns to copy whatever decisions the Monte Carlo tree search would do, right? And similarly, you can also calculate your value loss. You can calculate the total loss using the sum of those, and then you'd back propagate that loss. In this instance, it's an actual back propagation, and you'd update those weights. Any questions?
Didn't we only learn temperature here, not predictive? Or you didn't understand?
No, we'd learned both, because the loss is actually the total sum of two different losses. And when you build a think of how the computational graph is built, right? When you forward pass, you get outputs from both of these, and then when you back propagate, and then you obtain a single loss value, right? Now, when this value goes back through the computational graph, it first goes to these two values, right? And then the value part goes to this value, and then when you back propagate that, it actually update the weight from here, right? So it will update this, that, and the first part will update this, and then this, that, right?
Can you show me the value loss again?
Yeah, so the loss term would then traverse through the predicted value, right, which comes at the output of the value network. And now when you pass that backward, you'd go through the value head, right? The interesting thing is that when you backpropagate this one single loss, the body part actually updates itself twice, right? Because one part goes through the reactor, the other part goes through the grid. Any other questions?
So you this whole Monte Carlo thing every single time you update the weights. Wouldn't this take a very long time?
Yeah, actually, it takes a lot of simulations. It's very heavy. And what was your specific question? Wouldn't you do Monte Carlo for every?
So you use Monte Carlo every time you update the weights, every epoch.
Yeah, you actually do many Monte Carlos before a single update. Because just for this memory buffer to be full, just for a single entry to be entered into a Monte Carlo buffer here, in my example, this is worth 800 simulations. So in total, there's 2400 simulations here, right? So because you discard after you traverse from the root to the first child, you discard everything else, right? You just did all this simulation just to make one decision, and then you discard and you repeat those for the so when you get to node A, you repeat those 800 simulations again and see which one get the fresh new statistics. Okay, now we'll take a look at a more algorithmic view of this whole business. So at the very core, for a bunch of iterations, we followed these 4 steps, right? We use that PUCT formula or the UCB formula to select every child and then traverse to the boundary of the visited nodes, right? And then when we went to that boundary, we looked at the unvisited nodes and then we expanded our leaf node by 1 addition, right? After we had that addition, a single addition, we took this whole state and then we passed it through the value network to obtain some kind of a value, right? And then, although I say backprop here, it's actually just the updating of the statistics in those in all the nodes that led up to that child that we have currently, right? And this is the most innermost part of the algorithm. And now, after you obtain that, you'd use those statistics somehow using that. And yeah, there's the temperature parameter here as well. Yeah, you use this statistics along with the temperature parameter. Again, if you guys remember, if the temperature value is really higher, what happens? What happens to this distribution?
It's flattens out, right?
Yeah, it becomes more flatter, right? And if the temperature value is lower, this distribution becomes more sharper, right? You use those statistics to obtain a policy, which is a distribution across this particular state. And then you append that. You did all these simulations just to append this one single memory to your buffer, right? And currently you don't know the reward yet because you've not terminated, right? So you have this placeholder question mark there in your like buffer entry, and then you sample the next action to take. You move to that next action. Apply action basically means you go to the next action, and then you increment your time steps. You go to the next child, and then you repeat the whole process again, right? Yeah, you repeat this process until you get to the terminal state, right? And also, it might be a little bit confusing here because you could actually go to terminal states when you're running this simulation, right? But then you'd have to reach the terminal state here in the outer loop to be able to exit out of this. Does that make sense? When you're updating these statistics, you could actually reach to a terminal state before, right? But then when you're making use of that statistic to expand by 1 node, only then if you reach the terminal state, the algorithm would end. Yeah, only here you'd end. But when you previously got these statistics, you already may have possibly gotten to terminal states many times. It's a little bit tricky, yeah. So that's the first part, right? And then now for the second part, I mean, if I'm doing transit network design, I would have to take all that take the final state, and then simulate and then get some kind of a reward, and then I would replace these question marks in the memory buffer with the reward that I got, right? And then after I got those reward values, I basically use some stochastic gradient descent algorithm to update the neural networks that I am using, right? Basically get the gradient essentially following a process. And one thing to notice here is that where's the reinforcement learning? I mean, where's the discount factor? Where's the TD error? Where's the where are those kind of things that you discuss in your standard reinforcement learning setup? Basically, what we did was we had this whole mechanism where we were just collecting some data and finding a way to add data to this buffer. And then later, when we have enough data in this buffer, we just used supervised learning to train these neural networks. It's actually much closer to supervised learning setup than reinforcement learning. And that's it. I hope you guys learned something. I was a little bit under the weather today, so I don't know if I was clear, but yeah. That's it. Any questions? Yeah, this was my first pass through this algorithm. So I myself have not built a lot